Hello, this video is on two important equations that we'll be using in this unit called the motion equations. And the essential question is, how do you create equations that will let you to find or calculate the average acceleration of an object, its average velocity, and the same equations can also be used to find the distance an object travels for the amount of time it moves. So when we think about describing a moving object, where it's been, where it's going, what time it's going to be at those places, we need a few new variables. The first is one we've talked about before a little bit, but we're going to use it a lot more in this unit, and that variable is velocity. We use a lowercase v to represent velocity, and it may have operators like delta or average as we move along with this. Velocity in general is defined as how fast something is moving, which is probably something you're familiar with. There's also a little piece that tells what direction it's moving, and we use positive and negative signs in physics, usually to indicate direction. The units for velocity are meters every second, and we usually write that m over s, although you may have heard it said meters per second. I prefer every because it's a little bit more descriptive, but it works either way. Or the units you're probably a little bit more familiar with are miles every hour, aka miles per hour. Any units that describe a distance moving in a certain amount of time are going to work for velocity. And in the image below is kind of just an example of, a slow velocity turtle and a high velocity rabbit, which you're probably familiar with. The second variable we're going to be using and that we need to define is acceleration, which is a lowercase a in an equation. And the definition of acceleration is how quickly an object's velocity changes, and also in which direction it's changing. Acceleration is a lot trickier to get a handle on than velocity. So here's an example of two cars. They both could have the same velocity, right? They both could be on the highway going exactly the speed limit, behaving themselves on the highway, so they could have the same velocity, but these two cars will probably not ever have the same acceleration, which means the way they got to that velocity was really different. That little bug got there in a lot of time, very slowly, chugging along on the highway, whereas the Bugatti Veyron can get to that same velocity much quicker, and that is the difference between acceleration and velocity. It's not about how fast you're going for acceleration, it's about how fast you speed up or how fast you slow down. That's what acceleration really is. The units for acceleration are meters per second every second. So it's how much is my speed changing, which is meters per second, in 1 second. And that's why the units look a little bit funky for that one. All right, so the first equation we're going to derive is an equation for average velocity. If you wanted to know the average velocity of an object, what two variables would you have to find out or measure? So just think about you're at a swim race and you want to know how fast the swimmer is going. What things are we going to have to know? I think most of you have either done this before or it's pretty logical and intuitive that what we would care about is how far that swimmer is moving. In other words, the distance that swimmer travels and the amount of time it takes the swimmer to get there. So we have our dependent variable, which is average velocity, and two independent variables, distance traveled and time it takes, and that's what we're going to be using to build our equation. Okay, so in order to figure out the equation for average velocity, we need to figure out how each of our independent variables will affect the average velocity, which is our dependent variable. So to do this, I like to do either a series of experiments or thought experiments to try to figure out how changing just one variable by itself is going to affect it. So the first question is, what would happen if two objects or people covered a different amount of distance in the same amount of time? So this is a photograph from a wheelchair race. Presumably they all started at the same spot. And at the moment the picture was taken, you can see that those racers have covered different amounts of distance. That racer on the left has covered a small, comparatively relative distance, and the racer on the right has covered a larger amount of distance. So then you ask yourself, which of these racers has more velocity? And hopefully it's pretty obvious to you that the smaller the distance we cover, the smaller the average velocity was over the course of the race. Whereas that other racer who covered a larger distance, that's going to be a larger average velocity. So that should hopefully feel to you like linear relationship. There must be a linear relationship between delta D and the average velocity of those racers. We need to do the same thing for our other variable. So our other variable is time, or delta time. We need to know if we have two people that have covered the same distance now, okay, but they do it in different amounts of time, how does that affect the average velocity? So this is like a scoreboard from a swimming race, and it's a split. That means it's telling you how long it took you to go a certain distance. So everyone's gone the same distance, but they're covering it in a different amount of time, basically. So you see that racer in the middle has the smallest time, 1:38, and one of those racers at the bottom covered the same distance in 1:45. So what does knowing about these times tell us about those racers' average velocity? Well, if you've done any kind of running or racing events, you know that you want a small amount of time. That means you're going faster. The lower the time, the faster you went. So small time means we actually covered that distance with a high velocity, and a bigger time means that our velocity was much lower. So hopefully this to you jumps out again. This is an inverse relationship between delta T and V average, because the bigger the time, the smaller the velocity, and vice versa. So now that we have our two relationships, assuming those are the only two variables that matter, we can go through the process of building our final equation. Remember, you start by putting your dependent variable on one side, my V average all alone on one side of the equation, and an equal sign. And then on the other side of the equation, we're going to put any linear relationships on the top. So delta D, which is linear, goes on the top, and any inverse relationships on the bottom. Delta T was an inverse relationship, so it's going to go on the bottom of that fraction. One little note about this. Why are these math operators such a big deal? Why do I bother having that word average or the deltas in? Well, because objects don't necessarily keep the same speed during their entire journey, right? If you've ever driven in a car somewhere, you know that your car speed goes up and down and changes all over the place. It's really complicated to deal with speed that's changing all the time. And it turns out we don't actually care what your speed is at any moment. All that matters if you want to figure out how long it's going to take you to get somewhere is what's the average speed that you travel during that time. So it's really important that you note, though, this is V average. It's not V initial, it's not V final, it's not delta V. Those are all, they could all be totally different things. What this equation is going to tell you is what is your average velocity during a chunk of time. The other thing to note is that those D and the T have a delta in front of them. Okay, remember that delta means change in. And the reason it has that is because to have any speed, your distance has to be changing, right? If you're staying at the same location, no matter where that location is, your velocity is 0. So if your distance isn't changing, then you're not going anywhere. So we don't care where the object is. That would be the plain old distance, or what time we're doing this at. That would be the plain old time. What we care about is how much distance is covered or traveled, which is delta, and the amount of time that passes, which is delta T, for that as well. So please pay close attention to those math operators and make sure that if you're plugging into this equation, we're going to be using the correct values. The second equation we're going to derive or figure out today is for acceleration. So if you wanted to know someone's average acceleration, what things would we have to find out to figure out how much are we speeding up every second? How much are we slowing down every second? So to do this, you'd have to know how much your velocity is changing by, and also how much time it is taking to change. So this is a little bit different. We don't care about where you are in your distance, right? We care about is what your velocity was at a given moment and what it was at another time, and how much it changes in a certain amount of time. So I'm not going to go through this equation derivation in quite as much detail as I did the last one, just to save time on this show. But I do want to talk about what are the relationships between the dependent variable A and the independent variables, which are delta V and delta T. So if we think about a cheetah, which is an animal that we know has a pretty high acceleration, it can go from 0 to 60 very quickly, that it needs to do that to catch its prey. So we know it has a big acceleration. What is true about the cheetah that makes that true? Well, number one is that it changes velocity by a lot, right? We can start at rest and get up to speed of 60. That's a pretty big change in velocity compared to other animals. And so that tells me that the bigger the change in velocity, the bigger the acceleration is likely to be. There is a linear relationship between the two. And this is often why people sort of mix them up, because we know that things that can change velocity fast have a big acceleration, and vice versa. But it's not really the velocity that we care about, it's the change in velocity. And we'll do some more practice with that a little bit later on. The other thing that matters is how much time it takes that cheetah to get up to speed. Now, a cheetah would not be a very good hunter if it could get up to 60, but it took 12 minutes. Well, by then, right, the gazelles are gone. So the cheetah has to both get up to that fast speed and do it in a very short amount of time so it can catch its prey. So the smaller the time, the higher the acceleration of the cheetah, which makes that an inverse relationship. So we're going to combine those two relationships together to come up with a final equation. Remember, we put our dependent variable by itself, and then our independent variables on the other side, the linear on the top, delta V, and the inverse on the bottom, which is delta T. Again, a brief mention about those math operators. This one is really important. You gotta only use delta V in this equation, because if you use the plain old V, you're gonna get a completely different incorrect answer. If an object is moving at a constant velocity, that means either if it's sitting there at rest, or if it's like a car on the highway on cruise control, so we're moving at 50 miles an hour but constantly, okay, the delta V value is actually 0 for both of those cases. And that means the acceleration is 0. And that's a weird thing, because you probably know that a rock sitting on the road has 0 acceleration. But to think about a car that is moving but is not changing its motion, that also has an acceleration of 0, even though its velocity is definitely not 0. So it's really important that you can separate those things, and the thing that helps us see in the equation that they're different is that delta. It tells me that I have to have a changing velocity in order to have any kind of acceleration. So in conclusion on this, it is possible and even common for objects to be moving but not accelerating. Okay, so that's pretty important. All right, we've reached the end of this video, so please take a few minutes to revisit the essential question, which is, how can I create equations that allow me to find the average acceleration, the average velocity, the distance an object traveled, or the time the object is moving? We've come up with those equations, and we will be talking about how to use those equations and practice with those equations on a future video. Little comic for your time. Thanks for watching.